Good afternoon. Welcome, everyone, to this first talk for the EAGE Seismic Interpretation community. Hopefully, many dedicated talks will follow. This session will be recorded and made available on our EAGE community's YouTube channel. Please mute your microphone and switch off your camera to spare the bandwidth for those with a poor connection. Questions will be answered after the session. You can leave your question in the chat if you wish. Please let me introduce you to Sebastien and James for their Innovations in Seismic Interpretation talk, Broaden Your Horizons.
Thank you for that. Yeah, so let me introduce myself. My name is James Lowell. I'm the R&D Director at Geoteric.
Yeah, so good morning, good afternoon, good evening, everyone. I'm Sebastien Lacaze. I'm the CEO and the co-founder of Eliis. I'm happy to present you this latest innovation in seismic interpretation.
Brilliant. So yeah, let's crack on. So during this talk, what we're going to do is go through an overview of some of the classical methods, give some examples from a number of companies on established and emerging technologies. Question, what is the industry looking for? And then we'll close with some conclusions and perspectives.
Yeah, so thank you very much, James, for this introduction. So I will start with the overview of the classical methods in interpretation, also to see their limits. So just for you to start is just the purpose of seismic interpretation is for what, why? So to primarily evaluate and analyze the seismic reflection data, to detect and delineate the position of prospect leads, and characterize hydrocarbon reservoirs. So these are, let's say, the main objectives of the seismic interpretation. So, and then we have underlying disciplines. We have two main underlying disciplines at the core of the interpretation efforts: seismic geomorphology and seismic stratigraphy, which feed directly into subsequent domains such as structural and property modeling. So seismic interpretation is really at the core of the workflow, and this is the main input to really help us in the decision-making process. Then over the past years, of course, interpretation has made some progress, and classic seismic interpretation methods have generally required an intensive and often laborious process of manual picking and auto-tracking, single horizons and individual faults within a seismic volume or a set of 2D lines. Then, of course, the emergence of seed auto-tracking tools, which correlate wavelet amplitudes, have been around since the late 90s. So although they improved upon manual picking and gradients, their application was limited to regions showing either a clear seismic reflection or having a relatively simple geology. So more recently, the seismic attribute analysis has brought a real step forward and has also played a pivotal role in the 3D seismic interpretation, particularly for opaque three-dimensional seismic data, where attributes are indispensable for visualizing and characterizing reflection properties. However, these classical approaches often involve interpreting and capturing a subset of the possible horizons, faults and stratigraphic detail contained in a given 3D seismic volume, relying on subsequent stages in a broader subsurface workflow, such as modeling, to establish the interrelationship between interpreted objects and hard data. So it's just an example to show you, of course, a list of attributes which are very classical, from, let's say, seismic to sweetness, which is a kind of a derivative of the RMS amplitude or of the envelope, instantaneous frequency or instantaneous phase, and also the polarity attribute, which is widely used.
Yeah. So you could ask, with those advances in seeded auto trackers and with the attributes that we've seen over the coming years, why is horizon interpretation so difficult? Because when we think of often seismic events, we can imagine, as the examples here, seismic data with no faults, no noise, no unconformities, salt, and very continuous reflectors, where each component of a peak or trough corresponds to a unique horizon. That, of course, is not always the case, or most likely never the case. So let's add a little bit more complexity. So just by adding 2 faults here, and you can see that the data quality is still good. The reflectors are largely continuous. You would, of course, expect such dominant faults to be picked up, but a naive approach might actually track that single event going through there, because it doesn't have the understanding of what's happening below or above. And that's where a greater understanding is required to understand multiple seismic events, to be able to put that greater understanding and know, should that event be continuous or should it shift? So using a combination of both horizons and faults together.
So why innovation is needed? First of all, we've seen lots of progress in different domains, in geophysics mainly. Seismic acquisition has been driving the technological advancement by acquiring ever more data to better sample the subsurface. It's actually been developed with different technologies, especially advanced techniques, broadband, simultaneous recording, full azimuth acquisition. So lots of progress have been made over the last decades on this matter. Then processing and imaging technologies are now making better use of these richer data sets, offering a greater image fidelity through broadband processing, full azimuth imaging, diffraction imaging, full waveform inversion, etc., etc. So now when we look at interpretation, conventional techniques in interpretation used to interpret, analyze such kind of data have often lagged advancements in acquisition and processing, limiting the translation of sufficient detail into subsequent modeling workflows. So those applications have also struggled to make use of the subsurface detail requiring decimation and sampling. So in order to manage huge data, also we have to process and downsample data in order to manage this data on local workstations. But now today this is the age of the cloud computing, the artificial intelligence, and the automation space, and it has already brought about let's say a lot of progress in the approach of the development of oil and gas fields, one in which data, people, and collaboration are keys to its future success. So now the challenge is much higher. So we need much greater innovation to actually force to exploit ever more data, more difficult hydrocarbon resources, with also fewer technical specialists, and also more challenges, especially regarding the energy transition, which is happening today, and where CCS, for example, becomes increasingly important in the investment decision-making process. So now let's have a look at these established and also emerging technologies which have been developed for the past decade. So I'm going to introduce you the Extrema method developed by the Schlumberger Research Center in Northwest Stavanger. So this method was developed in conjunction with the seismic DNA approach. So the method consists in a volume-based automated horizon extraction that utilizes lateral recognition of reflectors within structurally complex regions by studying the shape of the seismic response. The method actually reconstructs the seismic trace on an orthogonal polynomial basis, generating an analytical representation of the seismic signal. And it comes from, of course, the patent of Zondervan et al., which was developed in 1994, to actually extract the maximum and minimum of each seismic trace. So the external points represent all maxima and minimum of events in a seismic cube. And then the calculated coefficients provide a set of attributes describing the shape of the seismic signal at each of the extrema. So thanks to this polynomial analysis, it allows going at a subsample accuracy. Then for the wave field reconstruction of the seismic trace, we actually use a lateral recognition of seismic events through similarities in a waveform captured by the set of attributes. Then to extract, all these attributes are extracted along each extrema position. Then we run a classification in order to combine, merge these different patches. So the classification is run automatically to detect all the lateral continuation of seismic events. And then the attributes extracted along all extrema positions are classified using a sparse 3D classification with each class characterizing a seismic waveform. So then for the geometry extraction, this is an automated method to build based on primitives obtained from extrema classification. And then each class characterizes a seismic waveform. So by extracting continuous classes, the interpreter can obtain consistent horizon patches with a subsample accuracy, allowing a seismic horizon extraction, seismic bodies extraction, and fault displacement estimation. Then altogether, this data can be combined and used in a chronostratigraphic framework to really understand, of course, the history of basin of any, let's say, seismic data set. It has been the first technique to really have an understanding of, a global understanding of the seismic data using this chronostratigraphic approach. Then more recently, inversion, new auto trackers have been developed, and we're going to present you a technique developed by DGB Earth Science on a horizon tracker within a hybrid method using inversion and also auto tracking tools. So the inversion tracker is based on the flattening of the seismic deep field. And then by mixing this inversion technique with an auto tracker, it flattens the deep field and adds more snap seeds at several points in the inversion loop to stay on the same event. Okay, so by combining these both algorithms, interpreter can avoid holes as in a conventional auto tracking tools, and the inversion improves the phase consistency and fault handling. Okay, so this is a very good technique, which is a hybrid, as it flattens the deep field and then adds, let's say, more seed events, and then improves the consistency of the horizons and also manages pretty well the structural network, structural framework. Then, based on actually the horizon cube that also DGB has developed, this horizon can be injected in this horizon cube, which is a dense set of chronostratigraphic events, where, of course, the emission-based algorithms were implemented. And this horizon cube can be used for sequence stratigraphic interpretation, horizon slicing, strata slicing, geosteering, model building, impedance inversion, and also well-to-well correlation. And now I'm going to talk about the UVT transform developed by Emerson Technologies. So this is this technique, UVT transform, is the development of a curvilinear parameterization where the U and the V are the paleogeographic coordinates and honor the horizontal force flow. It forms a basis of true volume-based modeling, which can be used to transform seismic into paleogeographic space for, of course, interpretation and QC. So this technique actually has been used, even though it was first developed for for modeling application. It was used in seismic interpretation to QC, of course, the interpretation, and also flatten seismic cubes. So I will show you one example, which was also proposed by Broaden et al. From, of course, the same Emerson group, where they have actually created a set of horizons within a grid where each patch corresponds to certain polarity. Then the extraction of patches was launched, and then the parameterization of the time was done using the UVT approach. So this is a good example where when you mix complex algorithms to reconstruct the seismic space, to convert the seismic space into the geological space, and then when you actually assign each geological time to each of your events, then we can use the UVT transform to check, of course, the conformity of the events in the geological space, and then reverse back to the real seismic space using this same transform. So the same thing can happen, of course, when you model at different times. You can have, using this UVT transform, a view of the Earth at a specific geological time. So now we're going to talk about the emerging machine learning technologies.
Thank you. So we will be very shortly going through a similar scope. So going through some examples of the that using different machine learning technology. But I thought it was just worth for anyone who doesn't know that the term was first coined in 1949 by Donald Hebb. So that's a long time ago. In his work, The Organization of Behavior, where he presented theories of how neurons get excited and they communicated between each of the neurons in the human brain. So he basically came up with the theory that when you had multiple neurons and they fired together, they became fused and then wired. Now, since then, there's been a lot of work, and that the concept has grown dramatically. We now can say that the term in the modern age of machine learning is a type of artificial intelligence that allows a computer program to learn without being explicitly programmed to do so. And this is still, since the 1940s, a very active area of research. Has a lot of complementary techniques. So these can be grouped into three categories. Unsupervised, which is good for clustering; supervised, where you have training examples; and then reinforcement learning as well. And many of these techniques can be used for both types, for both type unsupervised and supervised. And also, they don't have to be exclusive. You can chain these techniques together to solve more sophisticated problems. I'm sure we all know this, but for to avoid any doubt, as I know artificial intelligence, machine learning, and deep learning are often used interchangeably, that artificial intelligence is the umbrella that encompasses everything. It is a program that can sense, reason, adapt, act, and essentially tries to mimic the behavior of a human. Whereas, as we've seen, machine learning is just a type of artificial intelligence that allows a computer to learn, and deep learning is a subset of machine learning. So at present, the advances in artificial intelligence have really concentrated on algorithms constrained to performing a single task. no difference in our industry as well. But to solve more complicated problems, such as seismic interpretation, a number of these independent AI algorithms can be developed to solve different parts of the puzzle, such as horizon interpretation, faults interpretation, facies classification, and then so on. You also might be interested that that now has been used within geophysics and geoscience since the 1990s. And although deep learning has got a lot of attention over the last few years, other machine learning techniques have been shown and proven to be very effective. So just taking a couple of examples, not necessarily purely in seismic interpretation, but this one here, for example, is a self-organizing map or a Kohonen map, which is one of the unsupervised learning methods. It's been used in this case to create some clusters of meaningful spatial information to understand mining. In this research, a facies modeling has been applied without any attributes. So a support vector machine was used to cluster the actual data, but based on dissimilarities rather than the similar characteristics that you might be expecting. Interesting research. I'm not dwell too much on it, but when applied to seismic data in the Iranian oil field, it was shown that facies modeling based on seismic attributes provided better results, but it was an interesting experiment anyway. So going on to deep learning, there's been a huge amount of work in the recent years. This study by Siming Wu, they have created a deep learning method for cemeteries, fault and horizon interpretation. The supervised deep learning network was trained on randomly generated structural models and were used to estimate the relative geological time and to detect faults. To train the network, the synthetic models were generated with multiple examples of structural patterns. But what makes this one different is they then applied random masks to simulate missing parts of horizon data. Although the training only was applied to synthetic data, their research suggests that the network could infer full structural information in regions without any additional structural information, because the network has learned the representation of the surrounding geology. So, and this work, they have actually shared what the network architecture is, and for anyone who's interested, it uses channel attention and multi-scale fusion convolutional network. But what that basically means is the network was able to combine features with different spatial resolutions, thus providing an uncertainty with a plausible range of faults and horizons, but that are conditioned to some existing known faults and horizon data. So that's actually fed in. The research did use ground truth geological models that were, as I said, synthetic, and they were extracting in the training some sparse horizons and faults. That sparse information they had found was enough to provide and predict a plausible geological model, but only when the folding and faulting of the structures were consistent with their input data, so their examples that they fed into the networks themselves. I mean, this research was only just published a couple of months ago, but it would be interesting to see where it goes next. So moving on to Earth Science Analytics, they have created a cloud-native platform for seismic interpretation. The platform uses machine learning technology to allow geoscientists to access and use all the relevant data to gain new insights in order to improve the interpretation of seismic data, to create 3D property models, and also to compute data-driven holistic volumes and prospects and fields. The technology relies on pre-trained models generated from their EarthBank's third-party structured ML-ready databases, but it also allows an end user to fully configure the networks themselves. Through the configuration, these networks can also be trained on local data, and once trained, that trained model can be used to interpret features on unseen data. It is then expected that you would export those results to other G&G applications for QC and QA. It's been shown that these techniques have provided more detailed interpretation than the manual methods, and has shortened the timescale from months to hours or days. So moving on to some established and emerging. So Geoteric have created a deep learning technology that's been advertised heavily, but to identify seismic faults and also to extract fault planes. And there's some new technology that is emerging for the automatic extraction of seismic events. The New Horizon technology works in collaboration with the AI faults to simultaneously solve this 3D horizon jigsaw. The results shown here have not included any manual editing. Allows even the most faulted seismic cubes to be processed. So the image that I'm showing here is for completeness. Only 100 events are shown, but it has processed all of them, and we're just showing the ones in the middle that have been color coded for ease of depiction and to see the throws on the fault. Also, the events have been thickened again for ease of depiction. So what you're then seeing on the right is just to highlight again, these is processed without any manual intervention, and by combining it with a color blend, you can see that by eye it makes sense. You're able to see that the events are aware and stop quite nicely at the faults. From that, you're able to generate a 3D model directly from seismic. You, Sebastien.
Yeah, thank you very much, James. It's very interesting, this model approach. At Eliis, we have developed the EAGE model approach for a long time, or relatively short time. And we truly believe that understanding globally the data using this global comprehensive approach is definitely key. And I'm very glad to see technologies moving in that way. What we have developed at Eliis a few years ago is a similar technique to convert the seismic data, the seismic volumes, or even 2D lines, in a geo model, geological time model, using a semi-automated workflow, where in this case, we use a grid of events where each node, let's say yellow dot is a patch, a small patch on a certain polarity. It could be a peak, it could be a trough, it could also be a zero crossing, but similar way. But the difference is here, we don't use an artificial intelligence technique or machine learning technique. We use automation, optimization to track these events in a grid where all these events are known to each other, and then we populate, we calculate an age, a relative age for all these events in order to get a geological time, as you can see in my right-hand side. So that's there's a process where we calculate automatically the values, and then we have actually inserted the geoscientist, the interpreter, in the workflow to help refining the model where it's too complex. So that's for the machines. That's what we call a hybrid workflow, where we use automation. It could be also artificial intelligence, and then of course the let's say the human input to update, refine where it's too complex for the machine. So just to give you an example, and that's the approach that was developed to be a semi-automatic hybrid, where automatic technique can give you a first solution, and then the human input will add is constraints. We call it constraints. It could be also a supervised technique to help the machine to learn more and more. And then I'm going to show you an example of the difference between full automation and also, let's say, hybrid workflow, where you, of course, insert, of course, the interpreter's expertise. Just in terms of work, when you let it run for the machine, this is an example of the XMOS data, which is well known in Australia. The full automatic workflow takes a few hours to compute, or depending on the machine, or let's say the computer, let's say, power you have access to. And then for this human input, it takes a few days, weeks, depending on the complexity of the process. But the result is the following. That's what you have is by running automatically, it's always interesting because you get the main, let's say, guidelines, you get the main picture of your data, which is anyway a save of time compared to classical approach. And then when you bring, let's say, the human knowledge, you can get, that's what we want to achieve, something which is real accurate, which can also have much more, let's say, impact for, let's say, the subsequent applications, especially in modeling. So the automation brings the interpreter to next level. That's what all of us want to do. All the technologies we have presented, we want to bring the interpreter to next level, and then we have to get use of this human intelligence to actually solve very complex problems and solve the challenge. And as I can say, you can see, of course, the balance, but in this workflow, we see, of course, the value of the people to bring to something very, very precise. We just have shifted the objective, where today it's being fast, but also being accurate. And then based on, once you have a model, which could be generated either with this technique, but other techniques, as actually James explained you before, the new actually way to visualize your seismic data is completely different. This is a new paradigm where you can, of course, look at the data through this geological space, whether it's obtained by the UVT, whether it's obtained by this geodesign, or the artificial intelligence technique. You can screen or the horizon cube, etc., etc. There are plenty of techniques, and it goes in the same way where we want to visualize the seismic information through the geological edges. So in this case, what we do is we extract the relative geological times, which are not anymore peak, trough, or zero crossing, not anymore seismic polarity, just a picture of the Earth at a certain time. And then we have continuous events. And the beauty of that is having this continuous reference where we can extract as many horizons as we want, okay? So this is a bit different from pure ISO slicing. And then by, of course, putting some attributes, classification, or even more spectral advanced attributes such as spectral decomposition, you can screen and do the stratified slicing. In this example, the same XMOS data, which is just simple RMS mapping that we have used to scan through data and, of course, identify your targets, create your prospect generation, portfolio, etc., and characterize your reservoirs. So this is all together. I mean, we want to bring the industry to a step further. So by bringing these techniques, artificial intelligence, machine learning, automation, the key is today that the interpreter has a different role. Of course, we don't, and we will not pick anymore the horizons as we used to do 15 years ago. But we are actually, we want, of course, to get use from these techniques, from these, let's say, advances in especially computation and also geophysics. But we want to bring the interpretation a step further. But for that, let's have a look to the needs of the industry today. And this is just an example of the return of experience that was shared with us by Chevron Technology in Center. And I'd like to thank Anne Dutranois for sharing this information with us. So the idea today is to reduce the time frame between, of course, reservoir characterization to modeling, static or dynamic modeling. Today we have two objectives, of course, time constraint and also less people, but also we have to improve the efficiency and avoid, let's say dry wells. So we have these two objectives, and seismic interpretation remains the fundamental step to succeed in this process. Just to show you the dream of the interpreter, and I would say even the geomodeler was, of course, one of the subsequent application is to have perfect faults with no missing pings, to have, let's say, faults that impact the free flow, geologically consistent and connected with the fault framework, where the compartmentalization is validated automatically, dynamic fits, etc. Obviously, this is a complex process. And today, hopefully, in the future, we will be able to achieve that in, let's say, a few iterations only. But today, this is where we are. It brings a lot. So we just an example that Chevron has shared with us, where we can clearly identify, extract faults, for example, thanks to machine learning, in a much easier way. We still need some editing and Chevron actually experience had to edit to refine the fault, which were automatically extracted, but still it's much more accelerated compared to what we did before. Same things were also done on the facies, to prediction of facies, using the similar techniques with machine learning to, of course, predict the rock types thanks to the well data and, of course, well seismic correlation. So we see lots of progress. And again, that's a good let's say results that are shared by operators to us to show us first what we need to achieve for the future, but also the progress we have made for the past years. So that brings us to ideas for the future. So today we have many companies working on this topic. This is what we see around seismic interpretation. It remains a crucial step for all, let's say, the downstream applications. And the collaboration becomes a key aspect for the success. So obviously, the new cloud environment, and such as UDU, which is let's say the cloud ecosystem, is a critical component in the future of success of automation, but also artificial intelligence. And then we believe it will facilitate the integration of digital solutions. So now for the emerging and the, let's say, acceptation of these technologies, today it relies mainly on the service sector to develop these technologies. And we have to find the appropriate and scalable technologies for the future needs of the E&P industry, and I would say for the energy industry in general. So the independent technologies are developing but complementing each other. It has been integrated into this common environment, just as USDU. But then we also believe that the interoperability is crucial from operators to standardize and find an appropriate and scalable for the needs, scalable, let's say, scalability, standardization of these applications is key to really fulfill the needs of the E&P industry. So these are the two, let's say, main critical points: is collaborations, interoperability between applications, and also helping or sharing more with let's say, the service sector, let's say, technology providers, to really understand what the needs are. And then also what important thing we have to take into account is, of course, the importance of human capital. Artificial intelligence is not a debate, that's everywhere, machine learning, and it's progressing very fast. That we have to, of course, get use of that, and it's already in our workflows. That's not a debate. But we know that these artificial intelligence solutions are not generic and often have to be customized to different business contexts, data qualities, data availabilities. So we know that we still need some interaction with the machine to make a good model. So that's where the balance should be found with human interaction. And we believe that it's key to understand very well how, let's say, interpreters, let's say, the human, this human intelligence, this human, let's say, understanding of the data is working to actually push back the limits. So today, we know that the road is very long to the target, having finding better reservoirs, more difficult reservoirs with a limited time. So we know that the challenge is very high, and we need both, actually, from one side, of course, to maximize the use of the machine and the automation, and then bring the right tools to let, of course, the interpreter bring his knowledge, and then altogether we make lots of progress. So that's just an example to also for the acceptance of technologies in the industry. And today we see that the, let's say, adoption cycle of technologies in the industry is relatively long. That's also one of the drawbacks what we experience today, where we see emerging technologies and their acceptance in the workflow, and we see a big gap. So what we believe is that from a, let's say, technology standpoint and tech company standpoint, we definitely need to have an hybrid, let's say, a mix between, of course, a geoscientist and now data scientist. And also we need to be able to address this skills gap and to really understand what the needs are with, from, let's say, the operator standpoint. But then on the other side, from, let's say, the technology adoption standpoint, we need to find a way to accelerate this integration of technologies in the companies. We believe that we will need many experienced specialists inside these companies to understand technologies and also understand the needs, internal needs of the company, depending of course, the different objectives, targets, and also prospects. And then this will be the key to actually have an optimum use of these emerging technologies within a short time frame. And just here on the right-hand side, we show you just an example of adoption cycle where when you have from the early adopters to what we call the late majority, the laggards, that's where you get the whole market. When you have all these communities, families of people, that means you have the whole market. And this is generally a very long process to actually get at least early majority and also late majority. So that's something we have to probably work together. And of course, where the idea of integrating more technologies into a new, let's say, cloud space will be probably beneficial for all of us. And then just to conclude on this presentation, this outlook and the perspectives, is that what we can see today is that all these advances in this core specific and geoscientific workflows, and also the broader use of AI, artificial intelligence, machine learning, deep learning technologies to improve this cross-discipline integration can potentially, but I think will definitely change the way the geoscience industry operates and works today. So we believe that this is a major step we are experiencing today, and we will not work as we used to be even a few years ago. So today, what we see is after this terrible pandemic, and also given, let's say, the high level of objectives, climate change, let's say, the need of new energies, the need of CCS, storing and sequestrating the carbon, we have to de-risk and speeding up even more all, let's say, the business processes. So exploration, development, and also the gas field production. So this is where the collaboration will remain a key point. Energy technologies, but also data ecosystem have evolved in many ways. Okay, so many different companies from different sectors are now playing on the same space. But these companies, these different sectors, may have different priorities. So we need maybe to align to avoid any conflict between, let's say, these different actors. So that's also something which has to be balanced. We are today, and among the technologies I presented you, we have big companies, small companies like us. James and I, we are relatively small compared to the big players, and also now we also have the digital world playing in the space. So we have to find the right balance to make sure that everybody can evolve at its own pace and also can reach its own objective. And we truly believe that OSU will and may become a major change to let these actors actually play on the same ground field, where because it's data centric, and where we believe that the companies can interact in a more collaborative way. So just to conclude, so all these advances, technologies, automation, artificial intelligence, within this upstream exploration production, highlight anyway the importance of the geoscientist to successfully develop, implement, and benefit from. So we know that the input of the geoscientist in the workflow is key to drive the process and ensure the success of every, let's say, project. But the idea is to spend less time in manually picking, but more time in understanding, really more time in bringing the knowledge for the geoscience work. And then the idea is to use this knowledge to spend, of course, more time in understanding, analyzing, and asking questions. Why is the horizon like this, etc. So that's important to know that today the geoscientists will drive, but the machine will help a lot to push back the limits in our industry. So we like James and I to acknowledge all the persons who have participated to this presentation and for sharing the information. So we like to thank all of them for, let's say, contribution and also openness. Pierre Le Guen from Schlumberger Stavanger Center, Lucas Moser from Earth Science Analytics, Xibing Wu, professor at the University of Science and Technology of China, Paul de Groot from DGB Earth Science, Bruno Doribe from Emerson, Anne Nutranois from Chevron Technical Center. So thank you very much. We are very happy, James and I, to present you this latest advances in seismic interpretation, focused especially on horizons. And of course, we have some time for questions if you have some.
So there's a question in the chat from Jeanette. Where do you think Geoteric and Paleoscan Eliis are on the scale of use beyond early adapter stage? Speaking as a former power user and early adapter of both.
Good question.
Yes.
I'd say certainly from the geoteric side, the technology that we've been creating over the last 4 or 5 years, it's now starting to get into a service mode. So we are taking projects on, but it's too early to kind of say, as it hasn't been launched yet, how that will be, what kind of scale the adoption would actually be.
Yeah, I would say from my side, from Eli's side, I would say we are still at early adopter stage. If I can just come back on the adoption cycle. Yes, we are still at this stage, obviously, and we see, of course, it's hard to move. We understand that for, let's say, users, it's hard to have so many technologies available, and we have probably to think of simplifying things because today there are so many applications that the interpreters do not know exactly which one is good for, etc. So that's where this integration is important, to understand where you are in the space and to not overlap too much in applications. But yeah, we are still at the, I would say, the early adopter phase.
Just to add to that, on terms of the different technologies, it doesn't mean that you can't apply competing technologies to understand risk. So if you have 2 processes that are mathematically doing, or they're mathematically different, and they should be giving you comparable results, where they aren't comparable, then you have some additional reassurance. Where they are different, that's where the interpreter can then spend extra time. I think, as Sebastien was going to say, the shared data platform, and having the initial data all in the same format, then does lend itself to that type of work.
Yeah. Thank you, James, for precising the answer. Of course, as you can see, this is a good example where 2 companies can share the same topic, same presentation. Obviously, we see today that between, let's say, software providers, technology providers, there is more and more, let's say, collaboration going on. Geoteric and Eliis is a definitely good example. We've been collaborating a lot, even though we are overlapping at some point, but we know the approach is different from both sides and can bring all together an answer. And we at Eliis, we believe we don't have the answer, we have part of the answer, and Geoteric has also part of the answer. Obviously, there's the space of today is that we talk to each other. That's probably a different paradigm where 15 years ago, in technologies, there was a kind of, it was very opaque at some point. Today, there's lots of space for us to think, to exchange, and it's also challenging. We have to be better and better every year, but in, let's say, other way, it's also good for our science, where we can really push back the limits. That's one of the key to push back the limits, to be able also to collaborate, and that's why we put this slide where, especially on collaboration, where we believe that the space of collaboration is important. OSDU is of course one of the space which has been let's say open a few years ago now, and going on, and we are both of us very active in that space. But there are also spaces where we have to probably share as much as we can information to find some solutions, and also the understanding the client's needs, the operator's needs is very important. Today, as a software technology company, we don't have access to data. We develop techniques based on our own, let's say, data, or just public data set we have access to. And ideally, but I know it's complicated, it would be interesting to collaborate more with operators, to have access to more information, to understand and help them solving the problems. Yeah, so if there's no any more question, I think it's already 3 p.m. Corinne, let us know if you want us to continue.
I don't see any questions in the chat anymore. I'm not sure if anyone would like to ask a last question.
Yeah, this is Jeanette. I asked the previous question too. The image you showed with the Eliis image of the horizons and the faults, were those faults auto-picked? Are y'all capable of doing that now? Or, I mean, I know Geoteric has been working on it for a while. I was just really curious if that was all auto-picked. Thanks. It was wonderful. I really enjoyed it, and I love both softwares. So thanks.
Thank you very much for your question. So you mean the faults shown in the different slides, or?
Yeah, the fault shown in the next slide where you talked about the automatic interpretation and then how the geoscientist. No, one more.
This one?
Yes, this one, where you said automatic on the left. I'm curious, are all those faults and all of the horizon interpretation automatic?
Yeah, yes, they are. They are absolutely. So this is and then what we have done here, that they were automatically picked using what we call a fault plane attribute, which is based on the scanning, 3D scanning of the variance. And then there's a hybrid workflow where the interpreter can check some faults to cut them properly. But yeah, they were automatically picked. And today, if I speak on a general sense, all products like Geoteric and Eliis product and Earth Science Analytics products, etc. So there are a bunch of products that provide automatic fault picking. And if I can just show you these slides here, that's an example of another workflow for fault extraction. It remains, the key point is here still, we need to insert the interpreter, we need to include the interpreter to check the faults because there are always something you may miss. So you need the right QC tool. So that's where I'm not trying to emphasize this part of the workflow, but yeah, what I can say today, if you look at compared to 5-10 years ago, where fault auto tracking was just emerging, today it's getting more and more mature technologies where we don't pick anymore the faults as we used to. We get a fault set, fault extracted automatically, and we clean it. But we barely pick like we do every 5-10 lines. But by the way, on the faults, we're going to have a specific webinar probably in the next one, but we have to see with the group. One of the next webinar will be focused on the faults with all the technologies to extract faults with the different approaches. But that's key also, faults.
Questions.
Thank you for your question. Do you have any more questions?
So there are no questions in the chat anymore. I would like to thank you for your excellent presentation and your time. And I would like to wish you a very lovely day.
Thank you very much.
Thank you everyone.
Thanks to all of you, and thanks to all the contributors.